Dear children, hearty welcome to today's class. Last class, we were discussing about the different molecular interactions in liquids that are attractive interactions and repulsive interactions. In the last class, we discussed about the attractive interactions. Today, first we will discuss about the repulsive forces followed by the Lennard-Jones Toll-6 potential. The discussion and equation of Lennard-Jones Toll-6 potential. Now, let us see what is repulsive forces. We know that the repulsive forces are existing between the like charges. That means, if we have positive and positive charges and negative charges, then the repulsive forces will come, and the attractive forces will come when we have the unlike charges. Here we are more concentrating to repulsive forces. The repulsive forces means if we have negative charges, then it will be repulsive force. Then if it is positive and positive charges, these equal charges will repel each other and will have repulsive forces. Now, our question is that when the repulsive forces will exist, that is, the molecules in the liquid, the electron cloud of one molecule will come in contact with the electron cloud of the another molecule, then the repulsive forces will play a role. That is, if we have an electron cloud, if we have a molecule here and this molecule is having an electron cloud here, we know that the electrons are having the negative charge, and here we have another molecule, that molecule also having negative charge electron cloud, negative electron cloud. So, when these two molecules are coming in contact, then the repulsive forces will exist between these two molecules. Then the next thing is that when these molecules are come closer, then what will happen? The repulsive forces will be more. When the distance between these two molecules are less, then the repulsive forces will be more. That is, let us see here, the intermolecular repulsive forces will be more as the distance between the molecules decreases. The repulsive forces increases as the distance between the molecules decreases. Then, if we are forced to come too close to each other, these molecules, what will happen? The repulsive forces will be high. When this repulsive forces is too high, then that will be predominate over the attractive forces, then the system will be unstable. That is, I repeat once again, when the repulsive forces are too high, then that will be predominate over the attractive forces between the molecules, then the system will be unstable. So, this is about the repulsive forces, that is, the repulsive forces are between the electron cloud of the one molecule to the electron cloud of the another molecule. And if the distance between these two molecules are less, then the repulsive forces will be more. That is about repulsive forces. Now, we shall discuss about the Lennard-Jones Toll-6 potential, that is something related to these repulsive forces. Lennard-Jones potential describes the potential energy of interaction between two non-bonding atoms or molecules based on their distance of separation. That is, it describes the potential, the relation between the potential energy of the interacting molecules and the distance between the two interacting molecules. This is proposed by the scientist named Sir John Edward Lennard Jones, who is a British mathematician and theoretical physicist who lived between 1894 to 1954. We will discuss this Lennard Jones potential by an experiment. Here we have two rubber balls, one at this end and the other at this end. That means the two rubber balls are at very infinite distance. When they are at infinite distance, there are no interaction between them. When we allow this rubber balls to little more come closer, and the distance between these rubber balls is r. When they are at the distance of r, they have some attractive force between them. We are allowing these rubber balls to little more close together. Therefore, the force of attraction between these rubber balls are little more higher and till they reach an equilibrium distance. That is the minimum bonding potential. Now, we are allowing these rubber balls to a little more closer. That means that time these rubber balls will overlap each other. When they overlap these rubber balls, there will be no attractive forces, there will be repulsive forces. That means the balls will go apart. At that time, the force of repulsion will be greater than the force of attraction. Till now, we were discussing that about the rubber balls. Imagine that this is our molecule, atom or ion. Here we have one molecule or atom or ion, and here we have another molecule or atom or ion. When they are at infinite distance, there won't be any force of attraction between them or any interaction. There will be no force of attraction or there will be no force of repulsion. But we allow these molecules to come closer. That means when they are at the distance of r, there will be a force of attraction between them. And when the molecules will come closer little more, they reach an equilibrium distance and the minimum bonding potential is reached. And in the case of molecules, there will be a time the molecules will overlap. When the molecules overlap, there will be a force of repulsion rather than the force of attraction. That means when two molecules are at infinite distance, there are no force of attraction and no force of repulsion. That means the potential energy is zero. Here, the potential energy is nothing but the force of attraction, the sum of the force of attraction and the force of repulsion. So, when the molecules are at infinite distance, there will be no force of attraction, that will be zero, and there will be no force of repulsion. Therefore, the potential energy will be equal to zero when the molecules are at infinite distance. Now, we allow the molecules to come closer, or when they move, when the molecules move or when the atoms move or the ions move, there will be a time when they are coming closer. That time the interactions will start. The interactions, the attractive interactions, what we learned in the last module are dipole-dipole forces, dipole-induced dipole forces, induced dipole forces. So there will be these type of force of attraction and the repulsive forces also. This Lennard-Jones potential combines with the repulsion term and the attractive force also. It combines with the Lennard-Jones potential or the potential energy V. The potential energy V is proportional to 1 by the rth power of 12, and the attractive potential term is proportional to negative 1 by r power 6 or minus 1 by r power 6. Therefore, here the r has the power of 12 and the r has the power of 6, and this negative sign indicates that it is an attraction, and here there is a positive sign, that is the force of repulsion. Since this r has the power of 12 and the r has the power of 6, we will say this Lennard-Jones potential as Lennard-Jones 6-12 potential or Lennard-Jones 12-6 potential. This will say that these names are based on the powers of R in the two terms of the Lennard-Jones equation. Now we have the simplest form of the Lennard-Jones potential equation, that is, as we see here, that is nothing but VLJ R is equal to A by R power 6 minus B by R power 12. Now, here, as we saw earlier, the R is the distance between the two interacting molecules, and here we have A. This A and this B are constants. Now, our job is to find out the value of A and B, and V is nothing but the potential energy between the two interacting molecules. Here, the A is nothing but 4 epsilon sigma r power 12 and B is 4 epsilon sigma r power 6. When we substitute the value of A as 4 epsilon sigma power 12 and the value of B as 4 epsilon sigma power 6, we will get the equation VLJ R is equal to 4 epsilon sigma by R the whole power 12 minus sigma by R the whole power 6. Now, this term, this sigma by R power 12, the term indicates that this is the repulsive interaction term. And here, this minus term, that is minus sigma by R the whole power 6, indicates that is the attraction term. That is the force of attraction. This minus sigma by R the whole power 6 is the force of attraction, and the sigma by R the whole power 12 is the repulsive force of attraction. Here we saw that the value of A as A is equal to 4 epsilon sigma power 12 and B as 4 epsilon sigma power 6. So we have to substitute that here in this equation, that is VLJ R is equal to A by R power 6 minus B by R power 12. That is VLJ R is equal to 4 epsilon sigma by 12 divided by R power 12 minus 4 epsilon sigma power 6 divided by R power 6. Therefore, this equation becomes 4 epsilon sigma by R the whole power 12 minus sigma power 6 r power 6, that is the whole power sigma by r power 6, and this 4 epsilon is 4 sigma by r the whole power 12 minus the sigma by r the whole power 6. Where here in this equation we saw that other than r, other two terms, that is epsilon and sigma. Sigma is nothing but the closest distance between the two particles. Sigma is nothing but the closest distance between the two interacting particles, and the epsilon is the depth of the potential well. Epsilon is the depth of the potential well. Sigma is the closest distance between the two particles. This is the typical Lennard-Jones potential diagram. Here we have three curves, that means through three curves are there. One is here, that is something like this, and this is the potential well we have, and here we have the increase of repulsive force. These are the three important parts of Lennard-Jones potential diagram. And here when we draw this diagram, here y-axis we have potential energy and the x-axis we have r, that is the distance between the two interacting particles, and the diagram will be like this, something like this we have the diagram. And imagine that the one object is here or one molecule is here, and the molecule is A, and here we have one molecule, that is B. Now this A and B don't have any interaction. That means they are at infinite distance. When they are at infinite distance, the potential energy is nothing but 0. The potential energy is nothing but 0. And here this is epsilon, positive epsilon, this is minus epsilon. When we assume that the molecule is here, somewhere here, if we assume that when the molecule is somewhere here, it is getting an attractive force. That means now the molecule B is here, then this molecule is getting some force of attraction. Then the potential energy of the molecule is due to the attractive force or the force of attraction between the two interacting molecules. When this molecule is somewhere here, when this molecule is somewhere here, then the potential energy will be maximum. That means the distance between this A molecule and the B molecule. Now the B molecule is somewhere here, and here the distance between these two molecules are R distance, and here we have the potential well, here we have the well, and this is the minus sigma value, and here when the molecules are at R distance, the potential energy is due to the force of attraction. The potential energy is due to the force of attraction. That means that time the potential energy will be in negative value. Okay. Now, if the molecule is going somewhere here and the B molecule is somewhere, assume that the B molecule is somewhere here. When the B molecule is somewhere here means the molecule is getting, or the interaction between the two molecules is due to the repulsive force due to the repulsive force. That means here we have the maximum force of attraction. From there, this is increasing. The value is increasing towards the repulsive force. So, when the molecule is somewhere here, left of this well, then they are having the force of repulsion. That means the potential energy is due to the force of repulsion. Then assume that the molecule is somewhere right of this potential well. When the molecule is somewhere right of this potential well, when the molecule is somewhere right of this potential well also, it goes towards the repulsive force. There also the potential energy is due to the force of repulsion. Then assume that the molecule is coming to the potential well, or it is dipping to the potential well. When it dips to the potential well, there will be chance to fall down. The molecule is somewhere here or somewhere here. So that will be towards the potential well. The molecule will go towards the potential well. When the molecule go towards the potential well, the potential energy will be due to the force of attraction. Okay. This is the condition of the interacting molecules when they are at infinite distance, they are at the distance of or somewhere here, and when the molecule are at here, and when they are at the left, and when they are at the right of this well, and when the molecule is fall into the well. Now, we have the condition that when the potential becomes minimum, that means the dV by the differential of potential energy with respect to the distance will be equal to 0. That is the minimum potential energy the interacting molecules can occur. That is VLJ_R is equal to, this is the Lennard-Jones potential equation, VLJ_R is equal to 4 epsilon sigma by R the whole power 12 minus sigma by R the whole power 6. Now our job is to find out the minimum potential energy of the interacting molecules. The minimum potential energy of the interacting molecules are nothing but the differentiation of this potential energy. That is V R is equal to d by dr of 4 epsilon sigma by R the whole power 12 minus sigma by R the whole power 6. So, since 4 epsilon is the constant, 4 epsilon is the constant here, we will take out that here, and we have to differentiate the equation d by dr of sigma by R the whole power 12 minus sigma by R the whole power 6, and the differentiation of sigma by R the whole power 12 is, the sigma 12 is the constant, and now we have to find out the differentiation of 1 by R the whole power 12. That is, this 1 by R will become the R power minus 12. Therefore, minus 12 will come. Then the minus 12 minus 1, that means that is R power 13. Here this is sigma by R. Now we have to find out the differentiation of sigma by R the whole power 6. That is, we will get the 6 sigma power 6 divided by the R power 7. Here also in the case of sigma by R the whole power 6, the sigma power 6 is the constant, and here this will become R power 6. Then we will have r power minus 6, then this will be sigma power 6 into minus 6 into r power minus 7 it will come. Therefore, we'll get the answer sigma by 6 divided by the r power 7. Here we have 6 also. Sigma 6 is nothing but 6 sigma 6 divided by r power 7. Therefore, finally we will get the answer, the differentiation of dV by dr, that is the minimum potential energy of the molecules as 4 epsilon minus 12 sigma power 12 divided by r power 13 plus 6 sigma 6 divided by r power 7 is equal to 0. This is the dV by dr value. And here the distance r is nothing but the diameter. Sigma value is nothing but, sigma is nothing but the diameter, that is the closest distance between the two particles. That value is, here we have 2 power 1 by 6 sigma. I hope you understood Lennard-Jones potential. Once again I repeat here this diagram, that is the x-axis is the distance and the y-axis is potential energy, and here the potential energy is 0. Above that the value is plus epsilon, and in the below it is minus epsilon, and here we are fixing one object here or molecule here, that is A, and the another molecule first they are at the another molecule B at infinite distance. When it is at infinite distance, there will be no force of attraction and there won't be any force of repulsion, and the potential energy will be equal to 0. And when the molecule is here, somewhere here, the value is increasing. So here we have the force of repulsion, that means the potential energy value will be negative. And here when the molecule is here, somewhere here, that is the distance between the A and B are at the distance of r, that is the minimum distance between maximum force of attraction. There will have the maximum force of attraction. Here is the well. Therefore, the potential energy of the interacting molecules will be due to the force of attraction between the interacting molecules. And then when the molecule is here, somewhere here, left of the well and somewhere right of the well, in both cases the potential energy will be due to the force of repulsion, since the repulsive force is increasing towards here, and here also the repulsive force is increasing towards here. Then if the molecule is falling down into this well, then there will be chance that molecule can fall into this side and this side. Then when the molecule is falling this side and this side also, it is falling down to the potential well, therefore the potential energy will be due to the force of attraction. The potential energy will be due to the force of attraction, but it will not happen. Normally the molecule fall into the well only. Then the maximum distance, therefore the maximum force of attraction will be when the molecules are at the distance of r, when the molecules, the interacting molecules are at the distance of r. That means when V is equal to minus epsilon value, when V is equal to minus epsilon, that is the maximum force of attraction value. I hope you all understood the Lennard-Jones potential. Here first we saw what is the Lennard-Jones potential. This is the interaction between the two non-bonding atoms and the potential energy. The relation between Lennard-Jones potential is the equation is the relation between the potential energy of the interacting molecules and the attractive force and the repulsive force of the interacting molecules. That is the conclusion of this Lennard-Jones potential. Till now, we were discussing about Lennard-Jones potential. What is Lennard-Jones potential and the equation which is related between the potential energy and the distance, the repulsive forces between the two molecules. In this session, we discussed the repulsive forces between the molecules and Lennard-Jones Tolsyk's potential. We will see you in the next module with the properties of liquids. Thank you.